Let's continue with the question of why do we need complex numbers by examining this quadratic equation, which is ax squared plus bx plus c equals to 0. So basically again we want to find x such that the left hand side is equals to 0. In our previous example we have x squared plus 4, so we have the quadratic term, but we do not have the x term. So now if we introduce the x term here, which is b, the constant b times x, then the solution which we have studied in high school is this x equals to minus b plus minus square root of b squared minus 4ac divided by 2a. By plugging the constants in front of this x squared and x as well as c, we can find the x that solve the left hand side, such that the left hand side equation will be equals to 0. We call this, let's examine this square root of b squared minus 4ac. There are three different realization of the value b squared minus 4ac. When b squared minus 4ac is greater than 0, then we have plus and minus, so we have two solutions. When b squared minus 4ac equals to 0, we only have one real solution because it's minus b plus and minus 0 divided by 2a. So x will have only one real solution. Now when b squared minus 4ac is negative, then we have the complex solution. Okay, so this is what we know in high school, and we are using this. The fundamental theorem of algebra tells us that when we have a quadratic equations, we will have two solutions. If we have polynomial of degree n, we'll have n roots. That means n x's that will solve for this equation. So let's study the general quadratic equations. So we have x squared minus 2x minus 3, and when we solve for the x, then we realize that this radical contains a positive number, and therefore in this example we have 16, we have 2 plus and minus square root of 16, which is 2 plus minus 4, and then we find that minus 1 and 3 are solutions, and when we plot the equation, one crosses at minus 1 and the other side is 3. So this is two real solutions, very similar to our problem of x squared minus 4. Now when we change the equation a little bit, basically is that you see that we are going to move these curves upwards, and it only touches the horizontal axis in one point. So this is a single solution. We call it a repeated solution. Let's plug in the values and see what happens. Basically in the square root, we have these terms such that they become equal. 36 minus 36 equals to 0. So we only have 6 plus and minus square root of 0, which is 0. And therefore the answer is only 3. So there's only one x that will solve this solution. We call it a repeated solution. Okay, so it is still it's called a repeated root sometimes. And of course we have already realized that, hey, when we have certain values of the constant such that this square root sign becomes negative, then we do not know how to solve them. Okay, and of course in the last lecture we already saw that we can plug in here, which is square root of minus 1 multiplied by 3, which is square root of minus 1 square root of 3, and then which is equals to j3. Okay, so square root of 3, square root of 3j, or sometimes we call j as I as well. Now then we have an imaginary root, but when you plot, you actually cannot see where is the root. Later on we'll give you examples of how we can actually see where the root is in the imaginary axis. Alright, so let's revise this. The fundamental theorem of algebra says that when we have a polynomial of degree n, it can be factorized into this, and then there are n number of z such that this equation will become equals to 0. We call this the solutions or the roots of the polynomial. If you are interested to visualize the roots of the solution, you can go to slide number 16, where I will explain, or I will use the link here by Miss J Math to show you where are the roots of the equation such that the roots has imaginary solutions. Thank you.